Hello folks. Today we're going to begin what would have been the material that built up to test number 3. Now for right now, there is no test number 3 for the simple reason that I can't meet you. But I'm still going to be covering this material, alright? Anyhow, the material moving from this point forward would be the remainder of Chapter 5, this portion of Chapter 9, and these sections from Chapter 11. What we're doing today, just to point to it, according to the original calendar, is Section 5.4. On today, April Fool's Day. Anyhow, so we'll just be doing this today. Right. This is sort of a long-term perspective. What does Section 5.4 consist of? Let me show you. Oh, incidentally, if you want, maybe separate out your notes in your book by folding over a border like so. That's up to you. 5.4, and open this is in the frame, is about irrational numbers. And if you remember from last time, we had discussed rational numbers, which are essentially anything that can be made into a fraction, even if it doesn't look that way to begin with. There was a diagram that I had posted, and I encourage you to print. All right, this is the half of it that really is relevant. Imaginary numbers being this other side you're not responsible for. If you want, take the same thing that you have printed out from last time, and just recognize that we're going to be talking about this portion of it. All right, you can doodle on it to fill in notes if you want. All right, I'm going to sort of duplicate it here, what is relevant to us. All right, in our sort of family tree of numbers, we have real numbers and we have imaginary numbers. You're not really responsible for imaginary numbers, but if you're ever curious as to why instructions often specify these, right, it's because there is another category of real numbers. There are famously rational and now irrational. And in a nutshell, what distinguishes one from the other is this, right? Anything that is rational, right, can be a fraction. I think your textbook would probably prefer I say ratio, because it's a little less specific. Fractions are a type of ratio. But you get the idea, right? A number sitting on top of another number. Anyhow, irrational numbers can't be a fraction. It can't be a ratio. And there are two subcategories to this. Right, hopefully my green is up to the task. All right. There is one category. It has two conditions. And that looks pretty good, actually. All right. These consist of decimals, all right, that are two things simultaneously. They are non-terminating and non-repeating. What does that mean? Well, if you had a decimal and it would fit into the category adjacent, the rational category, that was something like this, 0.3 repeating. As you know, they use bar notation to abbreviate. That is really 0.333 forever and ever and ever. Even that comes from the fraction 1/3. You know, it has a pattern to it, an obvious pattern. Right? It may be non-terminating. This is an example of a non-terminating decimal, but it has a pattern. It does repeat. Right? If instead you have something that would seem to be a random sequence of decimals, of numerals, point something, 1, 2, 3, 4, 5 even. All right, ellipse, ellipse, ellipse. All right, that would be non-terminating and non-repeating because there is no pattern to it. All right. Anyhow, both of these conditions must be met in order to qualify as irrational. And there are some irrational numbers that you know already. All right, there are famously at least 2 or 3 of these. There's pi, 3.14159, whatever it is into infinity. Right? Now, granted, when a kid is in, let's say, 3rd grade, and maybe this comes up for the first time, maybe, when you're talking about areas of circles, they usually just sort of round this. They'll say, what is pi? It's 3.14. But just beware, that's an approximate for pi. It's a truncated, rounded incarnation of pi. Actual pi is non-terminating, right? Which means it is infinite. Right? If something is non-terminating, I wish this blue would cooperate, it is infinite. And as you can see, there is no obvious pattern to these numbers, right? It just seems to be random numbers. Anyhow, part of the reason why, in upper level math especially, they tend to use this symbol, this Greek letter for P, which we sort of mispronounce in English as pi, right? Is because it summarizes all of the infinity, even though we can't possibly see all of the infinity. It would be a futile effort. All right. There's another one. I mean, you've seen it most likely. The square root of 2. Right? The square root of 2 is 1.4142, I believe, something like that, into infinity. And it's not going to be 41414141. It just isn't. All right. There's a third one, which if you go into maybe teaching high school math, you're inclined to see this. Euler's number, E, which is 2.7182, something into infinity. Right. These all fit this qualification. They're infinitely stretching and they don't have a pattern to them. They're non-repeating. Okay. Anyhow, you're really only responsible to know these 2, right? Because they're going to come up today and in the homework that you see in my lab. Which, incidentally, last I checked, my lab was functional. I'm sorry. It's not anybody's fault if you couldn't access it, all right? The question now is, where do these originate from? Well, they really do come from geometry. And you'll see how so in a few minutes. This extra one here, E, Euler's number. Euler is a Swiss mathematician, I want to say, and his name is spelled E-U-L-E-R. All right, it's pronounced Euler. This, although you're not responsible for it, comes from finance. Anyhow, let's take a look at the first 2 especially. If you're curious, all right, let's discuss the origins of pi, all right? Basically, if you think of math as being, branches of math as being associated with a certain time in history. Pi is from the ancient world, you know, so I'm not a historian by any means, but if you imagine that ancient times are about the time history is recorded, so maybe 5,000, 3,000 BCE, up to maybe 500 to CE, the Common Era, all right? They were interested in geometry, because that was basically, you know, practical math for, you know, building things in real life, all right? Anyhow, I want to say that the Greeks are really responsible for pi, right? We all know famously this formula, the circumference of a circle, which is more or less the perimeter of a circle, or to put it more plainly, the distance around a circle. It's equal to these measurements. Well, it's equal to this constant, mathematical constant pi, times this measurement, which is diameter. Virtually everybody knows this, all right? But the truth is, pi originates from the rearranged incarnation of this, right? And I know what you might say, like, if you rearrange it, and I'm just going to perform a little basic algebra to rearrange it. You might remember, if I want to move something from one side of equals to another, I would perform the opposite operation. So the opposite of multiplying naturally would be dividing. And you would end up with this. The circumference divided by the diameter. Right? And you might say, well, geez, that looks like a fraction. Well, indeed, even though it is a futile effort, pi originates from the attempt to calculate basically what this ratio would be, right? If you could measure two things, basically the distance around the circle, and in theory as precisely as possible, measure across the center, right? That's all diameter is. This is across the center of a circle, and this is around. You can measure those two things. Perhaps you would get very, very close to this number, all right, which is known as pi. Now, truth be told, in ancient math, they didn't have decimal numbers, all right, but they did understand ratios, all right. Arabic numerals are at least from about maybe 500 CE, all right, and the Europeans didn't really start using them with any regularity until maybe the 14 or 1500s, something like that, 1,000 years later. All right, they were still using Roman numerals to do arithmetic. All right. Anyhow, this ratio, if it were perfect somehow, and it will never be, all right, would produce this number, all right, for any size circle. The division, all right, the quotient of the distance around it divided by the distance across a circle, any size, all right, will keep producing this number or something remarkably close to it, right? Anyhow, very difficult to measure a circle precisely, all right? Also very difficult to measure across the center even, all right? But if you tried, and they certainly did, imagine how you would go about that task. Here's a badly drawn circle, right? If a circumference is essentially a perimeter, all right, it's a distance around, how could a person calculate that? Even if you assumed the distance across the center was exactly equal to 1 unit, whatever it is, to make the math involved here really easy, just make it 1. You would still have to figure out the distance around it. And in that event, you'd be left to your own devices, right? You could start with the most basic polygon, which is a triangle, and you'd say, well, I could measure the flat sides of a triangle inside the circle, all right, and then see what the perimeter is. But it would be because of these huge gaps here. It'd be like the world's worst contractor, you know? Look at those gaps. What have you done? If you're like putting up like sheetrock or something, right? There's a big hole in my side of my house. If you did that, it would be very imprecise. It might not even make the number 3, right? So what would you do naturally? You'd start fitting in more sides, you know, a polygon with more sides. And by a polygon, I mean a regular polygon. A polygon that is an enclosed shape, flat sides, that are all equal sides, you know? So a square, you know? And this looks like I'm doing some kind of album cover art, you know? And you might get a little bit closer because the gaps start to shrink the more sides you get, but even that is not perfect, right? So then eventually what you would do is, well, I could do a pentagon, I could do a hexagon, and the more sides of your regular polygon, the more precise your perimeter, i.e. your circumference, becomes. But it's still going to be a futile effort because eventually, because of human, you know, shortcomings, you know, our eyes are not that precise, nor are our tools, right? You would have to shrink this down infinitesimally, you know, to as many sides as possible, all right, to get the accurate perimeter, i.e. the circumference, you know, a septagon, an octagon, you know, a nonagon, more and more sides, a dodecagon, all right? And it's always going to be, in theory, flat rather than what it should be, which is perfectly curved all the way around. Anyhow, that's why doing this, right, is never going to produce, you know, a terminating or repeating decimal, okay? Anyhow, this number is special, right? If I may be a little spiritual for a moment, right? God created the universe, right? Somehow the omnipotent being decided that this is important, all right? This and the irrational numbers. So save this, you know? Perhaps, and this is not correct, of course, but I like to think this way, you know? If God created the universe, you know, like this is one of the settings on the stove, you know? Like baking is what, 350 degrees, you know, which is an arbitrary scale anyway. All right, well, to make the universe, you needed this somehow, right? This and the other irrational numbers, all right, appear to be very important, all right? Not necessarily for, you know, any particular reason, but they show up a lot in nature at any rate. All right. All right, similarly, square root of 2. The square root of 2 comes from the Pythagorean theorem, really. What I should say, because I really didn't specify, this formula, which we were just discussing, is the circumference of a circle. Archimedes, in terms of who's who in math world, one of the people who was trying to get an accurate approximate for pi. All right? Pythagoras is another Greek mathematician whose work was not on circles per se, but on right triangles. If you had a right triangle, it would be the type of triangle that has that little box tucked into the corner, right? And this box basically means that there's a 90-degree angle. At least there's just that one, all right? Or you could say that it makes this perfect L shape, right, in that particular corner, all right? This is a right triangle. Pythagoras had discovered is that if you want to call the sides of a right triangle two things that are in common, leg and leg, right? Besides that form the right angle, the 90-degree angle, right? And then the side that is across from them, specifically a hypotenuse, they have a relationship, these three things, to each other, right? That is known as the Pythagorean theorem, right? If I were to spell it out, it would basically be this. That, I want a different color. Blue would be nice if it worked. Let's see. The first leg times itself plus the second leg times itself, that's what the exponent of 2 is, of course, would be equal to the hypotenuse times itself. Right. More concisely, it's usually written like this: a squared plus b squared equals c squared. This famously is the Pythagorean theorem, right? The relationship of the sides that are known as the legs of a right triangle in relation to its hypotenuse. And incidentally, the hypotenuse is always directly across from this box here, right? These two things, you could interchange them if you wanted to put this particular leg as A and this particular leg as B into the formula. That's fine, right? But a hypotenuse, which is the longest side, that is non-negotiable, right? That's got to be C, right? That's non-negotiable. These two things are interchangeable. Changeable. Okay. Anyhow, Pythagoras making the problem as simple as possible, which is to have a 1 unit wide leg this way and a 1 unit wide leg this way, right, produces this number ultimately, the square root of 2. I'll do that over here. Suppose you had a triangle that was on top of being a right triangle, also being isosceles, which means that it has 2 equal sides at least, right? An isosceles triangle can technically have a third equal side, but they really would generally prefer to call it an equilateral triangle at that point, right? But isosceles, by definition, has at least two equal sides. And they usually signify that by a little tick mark across the 2 legs. Right. This so happens to be a right triangle as well, which means that it has that 90-degree angle in it. Okay. Well, what's the easiest number in the world? Arguably 0, but I go 1 number higher. All right. Let's say that the dimension of this is 1, and the dimension of this is 1. Right? What would that make the hypotenuse then? Right? Let's plug it in and find out. I'm just going to erase this for a moment. All right, remember, A and B, as part of this formula, Pythagorean theorem, are interchangeable. So if you want to call this A and this B, that's totally cool. Right? My logic is this: think of this as B as being the bottom. All right? That is not the reason for the letter B, but it just coincides. It works well. All right? And let's think of this as A as an altitude. You know, it's kind of stretching it, but it does make sense. All right? A is an altitude, B is in bottom, if you will. Anyhow, if I insert the value of 1 here, it would have to be squared, which isn't going to change much. And if I insert the value of 1 in place of B, it would also have to be squared. Right? And the result would be this. 1 squared is 1 times 1, which is just 1. There's a plus in between. 1 squared again is just 1. And this is still equal to the opposite side as part of this relationship, c squared. If you added these together, naturally what you would get is 2. And you might be content at this point to go, oh good, mission accomplished. All right, I don't have to do anything else because I solved for the letter C. But do beware, right? It wouldn't be technically finished until you got it to the point of it just being C equals something. And right now, as it is left, it's not C, it's C squared. So what you would need to do is to perform the opposite operation for a cancellation effect, right? And do it to both sides. The opposite of squaring something is to what? Well, if you're not familiar, it is the square root. If you think of squaring as being a glorified form of multiplication, then square root is kind of a glorified form of division. Anyhow, whatever you do to one side of the equation, you are obligated to do to both sides. That is algebra. The consequence is that opposite operations essentially cancel. That leaves you with this C value, and then you have exactly what we were discussing, which is this, the square root of 2. Okay? That's where this comes from. All right? Pythagorean theorem, just like pi originates from the circumference of the circle. Now, it's worthy of discussing square roots at this point among other radicals. But before I do that, let me point to a handout that I was going to give you. There is amongst the handouts that I have for this particular section, a handout that looks like this. Right? It would be a good idea in the long run to sort of memorize these numbers: 1, 4, 9, 16, 25, 36, 49, 64, and 81. They're what you would refer to as perfect squares, right? A square, specifically the area of a square. If you had a square that had sides that are 1 by 1, you know that if you've calculated the area, it would just be that number times that number, right? That would produce 1. If you had a square that had a dimension of 2 by 2, right, that would be the number times itself, which abbreviated is using an exponent of 2. That produces the number 4. It literally refers to the geometry when someone says something is squared, all right? Similarly, there's the perfect cubes. A cube looking something like this. It has all equal sides, but you need to know 3 of these, right, to get a volume instead. This is for area, this would be for volume, right, which is the inside space as opposed to the inside area. 1 by 1 by 1 is 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, 4 times 4 times 4 is 64, and 5 times 5 is 125. These numbers, again, would be good in the long run to sort of memorize, right? Why? Because it makes math a little bit easier because you have some frame of reference. You can make predictions about something, all right? Anyhow, at least have the reference as we're talking about it. Okay? Let me erase this. If you're curious, all right, as about E, you're not really responsible for E. I'll just sort of show you the formula that it comes from. Just to complete that thought. Right. If pi comes from this, the attempt at getting a ratio that produces this number, or recognition of the fact that dividing these two measurements for any size circle produces this. And the square root of 2 basically comes from Pythagorean theorem. E comes from finance. It basically comes from this formula. Right? I want to say that this is for compound interest finance. Right? If you keep plugging in a number here, let's just say you started with 0, right? And then 1, and then 2. Did the arithmetic, the inside of the parentheses, and then squared the result, what you would get eventually is this number starts to appear, right? 2.71, right? Anyhow, these things come from geometry, and this comes from finance. Right? You're not responsible for the finance. This is more or less the kind of thing you might see in Algebra 2 or pre-calculus. All right, geometry is the more fundamental math. Okay. In terms of history, let's say that this is about 1600. All right. This is the ancient world. This is ancient math versus maybe, Renaissance math, or perhaps late medieval. I'm trying to think of what is that period that occurs after that. Let's see, 1600s. The Enlightenment, Okay. Here's a little summary of information. Let's discuss operations. So we're now broaching the subject of square roots and such. You're probably familiar already, but it's good to summarize. Remember, we have operations, and then in our lives, after the operations are taught to us, we are made to consider their opposite. In the long run, that is a good strategy because, as you know from probably having algebra at some point in your life, that in order to solve an algebraic equation, you take advantage of the opposite operation. Right? Before you come to school, what do they expect? They kind of expect, for better or worse, that a person knows how to count, right? Even if it's using their dirty, filthy hands, or take it off their shoe, and using their toes, right? So we have a natural intuition. We have a relationship with numbers, whether we readily appreciate it or not, at least up to 20, right? That would be the ideal thing if you have 20, 10 fingers and 10 toes. You count, right? When you come to school, they teach you a slightly more sophisticated form of counting, which is symbolic counting, right? Namely, adding, right? Which is signified by this plus symbol, right? They teach you the concept, the operation, and then immediately after it, they teach you the opposite operation, which is subtraction, signified by the minus symbol. And then it's sort of strategic from that point forward, right? This is maybe kindergarten, first grade, second grade, something like that. And then about third grade, at least I could vouch in my home life, they teach you a slightly more sophisticated form of adding, right? Which is, not so coincidentally perhaps, multiplying this symbol, right? Which is really plus just cropped, They teach you the concept, the operation, and then they teach you the opposite of that, which is division. In the United States, we tend to favor using this symbol for basic division, colon with a line through it. I've seen elsewhere that sometimes they just use the colon, and that's fine. In the case of division, there's lots of different styles to imply it, right? but this is the most basic type here. All right. And then a little bit further down the pike, you know, if that's maybe about 3rd grade here, then let's just say maybe 5th grade, 6th grade, they teach you a slightly more sophisticated form of multiplying, amped up, turbocharged multiplying, if you will. All right, which I don't really have a symbol to sort of signify this, so I'm going to just go A as in any number with a little superscript 2 up here. This would be squaring. It's multiplying in the sense that it is A times A, right? The number of iterations is the phrase we would use. I like to say clones. Send in the clones. That would be whatever number is here. This is telling you write this number in 2 iterations, 2 clones, and then as an afterthought, multiply. All right. They teach you the operation, the concept, and then they teach you the opposite of that. Who is they? Those are my Hawkins. Oh boy. Okay. Well, how would you signify that? For square root, which is what we've just begun discussing, there's this symbol, all right, which has a name. It's called a radical symbol, but I'm going to come back to that. Okay. I'm going to use some other letter, just not to fudge it. Let's just say you had some other number in here. If squaring something is an amped up, glorified form of multiplication, think of square root, which is what this is, as being an amped up, very specific type of division, if you will. Right? You know that in traditional division, right, you can write something like this. You would maybe draw that division box, and you'd have a number tucked on the inside, like, I don't know, 10. And depending upon what you put in the divisor, right, that will produce a number that is here in the quotient. Meanwhile, this is the dividend, how you would say it in English at least. Okay. If you have a square root, it asks a very specific question. Right? Square roots ask, what are the 2 identical factors that make this number, the number that would be sitting here. All right, there is a name for that. It's called a radicand, that I'm going to come back to that in a minute again. But this is the basic gist of it. All right, square root is asking you, what would the 2 identical factors be? And factors imply multiplication, ironically, perhaps ironically. They are opposite concepts. They're related somehow. All right, that would produce whatever number is sitting here. All right, that is basically as if and nobody says this, but it's true. All right, what would happen if the divisor and the quotient were the same number? Right? They don't bother calling them that. They call them factors, right? Because we're talking about it from the perspective of multiplication, but that's really what their job would be if you had something written like this. And you would put the divisor here specifically, and you would put the quotient here specifically. When you take a square root, nobody ever does that. Nobody writes anything here, right, as part of the sort of division that it is. Right? That's the left for coefficient instead. There is, I'm going to erase this just because I need the space, more of these into infinity, really. More roots and radicals This is an example of a root. It's a square root. This is the radical symbol. But where do they come from? Well, they come from raising this number to one number higher, all right, and beyond that. So the most basic form of exponents is what this is referred to as. This is an exponent. Is to go one number higher. So you have a number, well, maybe I should just use a different letter in general. I'll use C, say. Something cubed, right? They teach you the concept, and then they teach you the opposite of the concept. Right? You see this nice symmetry. Now, when it comes to the symbol that they have to specify the opposite of cubing, right? And that's what this is. This is, if this is squaring, having the 2 here, cubing, which is taking, 3 iterations, right? C, 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 and then multiplying, right? The opposite of that would be cube root. I'm going to put these down because they're a little cluttered here. This would be cube root. And they would designate that by tucking a tiny little 3 in here. It is unfortunate when it comes to square root, nobody ever puts the 2 in here, and I feel that they should, personally, and I do that for my own sake. But it is understood that if there is no number written inside the little check mark here, right, that it is in fact square root. I suppose because this is more or less the original concept, the OG of roots, if you will. All right, and this is just derived from that symbol. All right. So if you see a little 3 tucked in here, know that this is a cube root. If square root has 2 identical factors, then in theory a cube root would have 3 identical factors, and so forth into infinity, that produce this number. Okay. You can go like this forever and ever and ever. You can have a fourth, raising something to the 4th power, right? Let's see. The 5th power, there's the 6th power into infinity, but you're not really responsible for that. For this class, all right, you're pretty much stopping here in this realm. Adding, subtracting, multiplying, dividing, squaring and square root. Right. I just want you to see that there is a symmetry here. And it's the nice thing about math that we really should impart to our young people, our students, that there's a logic to it, that you'll see this pattern of how things are taught, through the subject, from being a little kid, 8 years old, into college. Anyhow, let me give you some nomenclature, some labels, because I've only alluded to that at this point. When it comes to square root, let's discuss labels, if you will. If you had this, the square root of 25, that's how you would read it in English, right? The square root of 25. Too much flair on that. Okay. A couple of things. The number, I'm just going to put the letter N here, all right? The number that really should be written here, whether it is or it isn't, like the number 2 isn't written here, but it should be. This is the index. which is basically the type of root. So if there's nothing here, assume that it would be a 2, in which case it would be a square root. If it's a 3 written here, in which case it would have to be, just to distinguish it from square root, it would be a cube root. Right? And the reason that it is important to identify it as such is because you want to know, well, how many factors am I looking for that are identical? If you have a cube root, as I mentioned, you have to have 3 identical factors, whereas square root just 2. Okay. The number that is sitting here underneath this symbol is referred to as the radicand. Think of this more or less as the guts of the radical, the inside. I love green, but unfortunately it never shows up. This 25, specific to this problem, is the radicand. Right, think of this as the guts, right, the inside of the radical. Right. This symbol, this sort of quasi-looking checkmark division box thingy, for lack of a better phrase. It kind of looks like a division symbol, right? But it has this little extra flair here. This is the radical symbol. Right, and the whole kit and caboodle, this whole thing considered at once is referred to as a radical. Right. It is simultaneously some type of root, and if you want to be more general, it's just referred to as a radical. Right. As for where you would put the answer, like I was saying before, in a division, a normal division, you would put a quotient here and you would put a divisor here. In the case of roots, you never do that. Right? They usually just say, well, if the question, let's just say that this is a square root, all right? And again, they would never put the 2 there, would just leave it absent. The question is, what are the identical factors? What times what, essentially, makes 25? Think about it this way. I like to draw little trees under the number. What are the 2 identical factors that make this number? And bear in mind, they have to be the same number, they have to be identical. There's only 2 choices, right? If you consider the factors of 25, there's 1 times 25, but they're not identical, right? The identical factors would be 5 times 5, right? When you write the answer, right, you really just write one of them, all right? And ideally, it is the positive, right? Because there is another option here if you think about it. This is where imaginary numbers would come into play. We are familiar with, in upper level math, the concept of signs, right? Of integers, of negatives and positives. And we know that there are combinations when you multiply them that dictate what the sign of the answer would be. For example, a positive 5 times a positive 5 would produce a positive 25. So positive 5, these being identical in terms of their digit and their sign, right, would produce this as an answer, equals positive 5. And that is in fact the preferred answer, right? Matter of fact, this is called the principal square root. This is preferred. All right. However, it is mathematically possible that there is a second set of identical factors that are not positive 5 that produce a positive 25, a positive 25 radicand here, the guts. And that would be a negative 5 times a negative 5. It is mathematically possible. A negative times a negative still makes a positive, which is why sometimes you see when you're looking at a textbook, this little abbreviation, well, they will tuck a negative underneath a positive. It means this: positive 5, comma, negative 5 are two possibilities. All right? That's being one and that being the other. However, for our purposes, it is the principal square root, the positive, not the negative, that we're interested in. Okay? And you just have to write equals 5 as the outcome, all right, if you're doing the actual arithmetic. Okay? Now, as sort of an overview of operations that would follow, let me draw you another quick diagram. All right. What can you do with radicals? There's several things that you'll be asked to do. I'm going to draw them adjacent here. Right. The first thing is that you could form an estimate of some radicals. The next thing is that you could form an approximate, which is almost the same thing. You'll see the difference in a minute. And then there's the ideal situation, which is this. You can simplify radicals. Okay. What is the difference between these? An estimate is more or less an educated guess as to what the solution, the answer would be to a square root of some sort. An approximate is using your calculator and simplifying is getting an exact answer, but it may not be especially satisfying because the radical will still exist as part of the answer. Anyhow, this is preferred, all right? These are things that people usually do just for the sake of comfort, all right? But simplifying basically consists of factoring. And that might be involving taking advantage of something called the product rule, which we'll get into, or perhaps the quotient rule. Notice this difference. Simplifying produces exact answers, which are always the best thing, right? A calculator will give you a highly precise, very, very accurate, but not correct, all right, answer. We think of a calculator as being an infallible sort of god, right? You're like, the calculator knows the answers, even if I don't, all right? But you have to sort of wean yourself off of it and convince yourself, listen, the calculator is only as smart as the person pushing the buttons, all right? So it will give you a very precise answer, a lot of digits all the way to the edge of your screen. But if you're talking about irrational numbers, remember that they're infinitely stretching. So it'll never give you the exact answer. That's why simplifying is preferred. Right? Especially if you had to involve some kind of radical as part of some larger, grander equation, you know, in engineering or in science. All right. Then there's operations. I'll give you the conditions of those now to add as part of this overview. There's adding and subtracting radicals. They have certain conditions that have to be met. Right? If you're going to add or subtract radicals, they have to be like. which means that they have the same index and the same radicands. In order to legally add them. Remember, the index is the type of root, so they have to both be square roots, right? And radicands is they have to have the same guts, the same number on the inside, right? And what actually gets added, or subtracted in theory, you just add or subtract the coefficients. The coefficient is just the number sitting on the outside, right? You have to make sure that the things you're working with match, that they like, all right? And once you do, you just add the numbers sitting in front outside of them. That's what you would call the coefficients, the numbers on the outside. Think of coefficients as being outside in front. When it comes to multiplying, which would be the next logical thing, it's a little less strict criteria that you have to meet. What you have to do is basically just make sure of one thing. They have to be same index. Which again is just saying that they have the same type of root or radical, same difference. All right, they have to both be square roots in order to multiply them. Okay. And what you're going to do in that instance is you're going to use the product rule, which we haven't gotten to yet, but more or less in reverse. The product rule is part of factoring technique usually, but if you sort of used it in reverse, it would help you as part of the multiplication problem. That basically just means multiply. Actually multiply. The last thing that we'll get to is division. I'm inclined not to use my green for the reason I have to complain. Let's see if it works. It works, okay. But when you're dividing radicals, right, they do have to be the same type. Same index. Again, same type, all square roots. All right. And what you may have to do is a technique known as rationalizing. The denominator. And if you know that, obviously, dividing is kind of looks like fractions, right? There's an obvious top and line and an obvious bottom, in which case there'll be a numerator and there'll be a denominator, a top and a bottom. Purely for the sake of etiquette, really, all right? Which, you wouldn't think in math that we would care how things look. We do, all right? We perform a function that is this technique, rationalizing a denominator, okay? Which we'll get to last. When you rationalize a denominator, basically is writing an equivalent expression that doesn't have the radical symbol in the denominator. It's considered bad etiquette, if you will. All right, that is an overview of what we will be discussing, and it will go pretty smoothly. Erase this for the sake of space. I'm going to use the same problem a couple of different times. All right? Let's start with this. All right? An example going sort of clockwise from my diagram of estimating. And estimating, shall we say, the square root of 20. All right. Now, the way that I've described it, and I mean it sincerely, is that estimating is an educated guess, all right, as to what the square root of 20 would be in the style of a decimal. And do remember, since this is not a perfect square, right, it's going to be an infinitely stretching irrational number. Right? Something that is not a perfect square is going to be irrational. All right? Which means non-terminating and non-repeating. But you'd have to stop at some point. All right? You'd have to chop off infinity at some point, even to use the number that you produce. All right, maybe as part of some multiplication problem. So we're just going to get an estimate, which would maybe be a couple of decimal places. All right. Here's what you would do. All right. You have this list handy, all right, of the perfect squares: 1, 4, 6, 16, 25, 36, 49, 64, 81, or at least memorize them. All right, and have that for a reference and go, okay, 20, all right, the number that's in the radical here, doesn't show up in this list, but it's between two of them. Draw this as sort of a model. I'm going to fill in these voids with question marks here. All right. Basically, we're going to ask ourselves, all right, which perfect squares is the radical, or the radicand, the inside guts technically, right, between I can't emphasize that enough. Between. Right? If we're working with this number, square root of 20, I'm going to put here. Just pay attention to this number. Right? Which numbers in this list of perfect squares is 20 in between? It's between 16 and 25. 16 would be on the low end, and 25 would be on the high end. 20 is less than 25, but it's greater than 16, right? So these are appropriately oriented. Okay, now how does that help us? Well, what is the outcome of taking the square root of 16? And if you need to, here you could use a calculator, of course, but there's another handout that I had produced, which I'll point at right now. It's this page. It's a little bit long. I just folded over in my notebook here. In the list of handouts that you can print out if you want. There's this page, which is the perfect squares, right, which would be the numbers 1, 4, 9, 16, 25 again, but from the perspective of a square root, sort of backwards. The square root of 1 is the same as saying 1 squared, which are opposite operations. It just gives you the inside guts. 1, 2, 3, 4, 5. All right, anyhow, these perfect squares, if you took the square root of them, produce these numbers, which interestingly are in numerical order. Square root of 1, 1. Square root of 4, 2. Square root of 9, 3. Square root of 16, 4. And so forth. Okay? If it helps, have that reference on hand. All right. Anyhow, to answer my own question, what's the square root of 16? It's whole number 4. What's the square root of 25? 5. So if this number, 20, the radicand, is in between this number 16, the radicand here, and 25 here, one could guess that the number in between them would be exactly 4.5. All right? It's an educated guess, all right? An estimate, all right? And the truth is, it's never going to be right. It's just going to get closer and closer and closer. Here's what I mean. This is what people would do before there were calculators, right? You'd make the educated guess, and then you would test it, right? If it's identical factors of 4 times 4 that make this number, then my educated guess of 4.5 times 4.5 should make this number, right? Look what happens if you do that, though. .5 times 4.5. 25 carry the 2, 22, placeholder. 20 carry the 2, 16 is 18. You'd end up with this. 2 decimal places. You get this number instead, which although is remarkably close, all right, 20.25 is overshooting it, all right? So then a person would naturally reason to themselves, all right, well, this is an overestimate, right? What is slightly smaller than 4.5? And then they go, oh, let me see, right? And I'd say, well, one number smaller than that would be 4.4. And then you'd go through the same business of, let me test it. 4.4 times 4.4, all right? 16, 17, placeholder. 16, carry the 1, 16, 17, carry the 1, okay. And you'd have 6, 13, carry the 1, 19. You'd have, and two decimal points, you'd have 19.36. All right? And then you'd say, damn, because what happened? In one instance, I overestimated and I overshot the goal here. All right, and in the second instance, I underestimated, all right, and now I'm a little too shy of it. 19.36 is close to 20, all right, but it wouldn't even round correctly up to 20. So then what do? You go, all right, well, what is in between 4.5 and 4.4? 4.45. And then you go, oh, good. Anyhow, if you had to sit here and do this forever, you'd be pretty annoyed, right? It's not impossible, but notice that your educated guess is getting longer and longer and longer. And it will be like that. How come? Because it's not a perfect square and it is irrational. So the decimal numbers, as much as I could do this forever and ever and ever, are never going to be correct. All right? It's just going to get closer and closer and closer and closer. As a matter of fact, if you straighten this out, what would you get? You'd get 19.8025. You get a longer decimal and you inch ever closer to 20, but you're never going to get there. All right? So, not to be, I sound like a villain, like, you're never going to get there, kid. All right? Don't be like that to your students, right? But just recognize it for what it is. It's not a perfect square, it's irrational. And you could fine tune this, add more digits here, and you get a better and better, more precise, closer to being accurate answer, but you're never going to get it. So to say this is squiggle equals, the square root of 20 is about equal to 4.5 is an estimate, okay? And that's fine, all right? If you recognize it for what it is, it's not the exact answer, it's an estimate. Everything's fair and square, okay? Now, what people normally do is they don't just settle for an estimate, they whip out their calculator and they go, ah, all right, the calculator is gone, all right? And this will give you the answer, all right? Just realize that because of what you're dealing with, an irrational number, even your calculator is never going to give you the exact answer because it can't, right? It's a mathematical impossibility. Here's what would happen for the exact same thing. If you typed, and I wouldn't fault you for doing it, an approximate for the square root of 20, here's what might happen. Depending upon what type of calculator that you have, all right, a scientific calculator, and this is the type that you really should have, all right, it's not wrong if you have something else, but for the sake of consistency, this was the type I'm kind of expecting you to have. There are certain buttons that you would be attracted to, all right. The second button, all right, which you notice engages anything that's written in blue behind the regular buttons. So if you wanted to do a simple square root, all right, you would hit second and then the square button here. This is exponent of 2. Notice in behind it there is a square root radical symbol. All right. So if you did this, second, and then you press this button on this type of a calculator, it would engage this feature. You'll see this show up on your screen, right? And then you would simply type 20, right? What you will get is this, and I'll do it in front of you. Let's see if the light is just so. I'm going to turn it on first. Let's see, on, maybe it was the on button. Hit second and then square, and the square root symbol shows up with a little parentheses. Then you type 20, I believe that is a 2, I'm reading it backwards unfortunately, and you could be a little bit twitty like me and close the parentheses. You could probably get away with not doing that, but I would anyway. Hit equals, and you see that you get some very, very, very precise, high precision here answer, but it's still not exact. It would be 4.475132, I think that's a 9, yep, it's a 9, 55, as I read some of that backwards. This is what you see on the screen. 4.472135.955. Just realize that's the edge of your screen. In reality, it stretches beyond that because it's irrational. What you end up having to do is either decide for yourself, or unless you're instructed, round to a particular place. So a lot of times I've noticed in textbooks they're kind of content with rounding to the hundreds place. All right, remember this is the hundreds, I should say, THS. All right, and you make that judgment call based upon what's sitting here. If the number circled is 4 or lower, in this case it's 2, so it's definitely lower, you just basically knock off infinity here. You round down. All right, and that makes this still not an exact answer, so I'm going to use squiggle equals, all right, about equal to 4.47, right? a calculator makes a better educated guess than what I had done, because I was content to just go 2 decimal places, well, 1 decimal place technically. All right, I stopped in the tenths place versus the hundredths. All right, this is not exact, but a little bit more precise. Okay. Oh, incidentally, if you wanted to do some other type of radical, like let's say you wanted to do cube root, there's a different button that you could press. I'll just give you this as a sort of side note here. There's a feature you'll see written on your calculator that looks like this, a little X tucked into a radical symbol. Let's just say that you wanted to do a cube root. There's a syntax, the order in which you have to enter information, unfortunately. So I'm going to clear this. You see a blanked out calculator? Over here, just above it where the caret symbol is, this upward pointing arrow, in blue, very, very faintly, there is X and then the radical. You would have to choose the index first. So if you wanted to do a cube root, choose the index first. So let's say that you wanted to do a cube root, you would press 3, and then you would go through second and then this button here, and it would understand that this is a cube root. Then you would type whatever the cube root that you're looking for. So I know that I want to produce one that works, so I'm going to use 8. Right? The cube root of 8 should be the number 2. All right? How come? Because 2 times 2 times 2, 3 clones of 2 iterations, whatever you like, produces that radicand. So I'm going to type 8, all right? And you should see it spit out the number 2. And it does. Good. There's 2. Okay? It's a little goofy. I mean, I wish it was a smaller font and it fit right in place of that X, but it's only that wide a screen. If you had a more sophisticated calculator like a TI-84, right, it would compensate. It would look much nicer. Anyhow, you're really just going to be doing square roots if you use your calculator at all for this class. Get a new eraser, I think it's getting really filthy. All right, let's do simplifying. I'm going to do the exact same thing, square root of 20, so you see the difference in the end result. Simplify the square root of 20. I could be with my markers and I'm drawing so nicely because of the filthy board I have here. This is going to produce an exact answer, which is why it is preferred. Just beware, the exact answer is just going to be something that involves a radical, unfortunately, still, just smaller numbers. It still preserves the entirety of infinity though, which is why it's a preferred answer. All right, now, the sort of background information you will need to know for this, I'll put above here. There are 2 things that you want to keep in mind. All right. First of all, there's the product rule. And then immediately adjacent to it, I'll put the quotient rule, but they're very similar. And they have sort of the same purpose. The product rule is to take some radical, right? And it may not be obvious that it's comprised of 2 things, but this is a model. And you're going to split it into 2 pieces. Treat them as if they were 2 autonomous things. Right? Because maybe one of them will be a perfect square, in which case you might escape the radical symbol. Similarly, if you had a quotient would look like this. Look like a fraction with the radical symbol wrapped around it. If it is a convenience for you, what you legally can do, according to the quotient rule, is separate these into two autonomous radicals, because maybe one of them will escape the radical. Right? When we get into rationalizing, there's a little added work, but this is the ideal situation, right? Take the thing that is grouped together underneath the radical symbol and break it up into two pieces. Take the thing that is maybe comprised of two parts and break it up into two things, right? There is a handout that I'm going to point to now that would be good to have on hand. This is a handout. It looks like this. This is more or less the objective. Right? When you're factoring using this product rule, you want the situation to basically be this. The first radical that you break your problem into is ideally the highest perfect square, or if you're dealing with cubes, perfect cube possible. Right? There are many factors for a number that you might see, like 20 has several factors, right? But you want to strategically choose the highest perfect square that is possible as a factor, all right? And then what you'll be left with in the second factor, the second chunk, is maybe a prime number, right? Or it could be a composite number that is just inconvenient to factor down even further. Like the 6 would be inconvenient is a perfect example. It's a composite technically, and it could be factored into 2 times 3, but neither of them is a perfect square, so you wouldn't bother, right? Let's do 20. Side here, here's a little thought cloud. Here are factors of 20. 1 and 20, 2 and 10, and 4 and 5. I'm just writing them like this, rather than in numerical order, because you know that factors come in pairs, right? 1 times 20, 2 times 10, 4 times 5. Thankfully, it's finite. There's not too many of them. Everything has a factor of 1, and 1 is, in fact, a perfect square. All right? It's in that list that we have established. All right? However, it is seldom, if ever, all right, a good choice. There is another perfect square in this compiled list of factors, 4. That's why when you're splitting this into 2 pieces, according to the product rule, you want to go with that choice. Okay? And the reason being, you've made these numbers smaller than what they were. So you've made some kind of progress. You've simplified, right? Even if you get stuck with this radical left behind, in the case of square root of 5, you will, unfortunately. This half of it, strategically, is going to have some number that escapes the radical, right? What's just the square root of 4? What are the 2 identical factors that make 4? 2, right? So therefore, the best answer is this. 2 times the square root of 5. That is the simplified answer of the square root of 20, and it is exact. Right? If you entered these digits into your calculator, 2 times the square root of 5, it would produce the same decimal as entering the square root of 20. So it preserves the infinity that is this irrational number, square root of 20. But it does so with smaller digits, so it's simplified. Somehow I lost my cap, so humor me for a moment while I pour out my thing here. There we go. A big coffee mug filled with markers. They're all drying out in spite of my trying to keep them upside down. Okay, here's proof. Right? If you took your calculator and you took the square root of 20, I'm gonna turn this on again. Here's the on button. The square root of 20, you don't have to put the parentheses, but so be it, being twitty, 4.47, we already know, right? If I type what we produced here, 2 times the square root of 5, and incidentally, because these things are pressed together, one assumes that they are being multiplied. You just don't bother doing that. And the name of this is a coefficient, right? The number in front. We'll see that if I type that, if it produces the same decimal of 4.47, it definitely will. All right, here is just to type 2, then I'm gonna have square root show up here. I'm gonna type 5, close the parentheses, equals 4.47. All right, it's the same value, all right, as the original radical. It's just using smaller numbers. Okay, all right. Sometimes it's not so obvious which to choose, so you which factors, so it's good to compile a list while you're working. Here's another example of the same type of thing. If you had to simplify the square root of 80, 80 has a lot of factors, right? I'm going to do it the ideal way first, and then I'll show you, even if you didn't start out in the ideal situation, all right? Even if you muddled through, you'll still get to the answer at the end, all right? When you're trying to factor this, all right, you're doing this. You're looking for the highest perfect square times some leftover, maybe prime or composite. This will be done in basically 1 or 2 steps. Right? It turns out that it's 16 that is the highest perfect square that you would have had to choose from. All right? Which may not be too obvious to a person, because even having the familiarity of multiplication tables, that's kind of outside the realm of familiar. All right? But it would be 16. And it would be 16 times, was it 5? Yeah. It's 16 times 5, carrying the 3, yep, it's 80. All right, here's just coincidentally, this leftover here is a prime number. If you factored it, it would just be 1 and 5. It's not going to go anywhere. This is a perfect square, though. It will have some number that escapes the radical. Square root of 16 is this. It's 4 times the square root of 5. That's the simplified exact answer of square root of 80. Let's say that you're a little bit, unsure, and you started out with some other choice. It's still going to work as long as you stick it out to the end. I'm going to just sort of in the middle here try to show you the ideal situation. To compile a list of factors of 80, it would certainly be 1 times 80, right? And then it's an even number, rules of divisibility, 2 times 40. And I'm going to try 3. The rule of divisibility for 3, which would prove that 3 is a factor, right, would be if the sum of the digits is divisible by 3. 8 plus 0 is 8. 8 doesn't divide nicely with 3, so not 3. We could rule out 6 then, naturally, as a possibility of a factor. 4 definitely works, right? 4 times 2 is 8, and you have a 0 attached to it. Same thing here. 5, and apparently it's 16. All right, 6 we already decided doesn't work. At this point, there is a rule for 7. I don't memorize it myself. I would rather just divide by 7 or memorize the multiplication tables. 7 times 7 is 49. 7 times 10 is 70. 7 times 11 is 77, which is just shy of this. And 7 times 12 is what? 84. All right. 84 would be overshooting it, so 7 doesn't work. 8 and 10 works. All right. Just check 9. 9 times 9 is 81. That's too much. When you've gotten from two things that are as far apart as possible as they are, 1 and 80, right? down to things that are practically on top of each other, 8 and 10, you've pretty much exhausted any possibility of accumulating any more pairs. All right. Anyhow, if you examine this list, everything has 1 as a perfect square. All right. 4, once again, is a perfect square. All right. But the best choice, and you want the highest, is actually 16, which is why you would choose that. Compiling this list is kind of a pain in the neck, but it's a worthwhile cause. You get your factors done without having to go back and forth. All right. If you did it a little bit more complex, you'll still get to the answer, but you have to be determined. All right. So let's say that you went with, well, I know that it's even, and you might intuitively go 2 in something. Okay, no sweat. All right. You have the square root of 2, and you have the 40. All right. And you know that 2 is irrational, all right, and it only has 2 factors, 1 and 2. You can't break it down further. It's a leftover for all intents and purposes. But 40 you can break down. And you might go, 4 and 10, all right, and that's cool. And you'd have a 2 here. And you'd have this bottom rung of this tree. And you keep going until you get, you know, at least something that could exit. Right? This would eventually, but I'm going to hold off on that. I'm going to keep factoring this other stuff. That's 2 on the outside. And 10 would be square root of 2 and the square root of 5. So you'd have all of this junk, right, lined up here. You have the 2 that escaped from square root of 4, and you'd have this stuff left behind. All right. I don't green. I wish green would cooperate. That's a 2, I swear. You can. Now notice what you got. You have 3 factors here. That would not be simplified, right? Especially by comparison, right? We do have something that is kind of similar to what the answer would be, square root of 5. Let's say you combine these back together. Sort of the product rule in reverse. This would be square root of 4 again, right? There's still this 2 that came from the original square root of 4, and that's not going away. Right? But recombining the junk that I have from this mess that's left over will produce yet another square root of 4. How come? Because it's really 16 that would have been the best choice. And there's still this square root of 5. Right? Anyhow, look what happens. I have the 2 that's on the outside, and I keep putting these multiplication dots incidentally because these things are all pressed together really. So they're all being multiplied. What's the square root of this particular 4? Another 2. Alright? These are both on the outside. They're the number that's sitting out in front, right? And this 5 would be the thing left behind, right? You're gonna get the same answer, but it would be more strategic again to go for the highest perfect square from the onset. Moving right along. Right. Let's do some adding or subtracting of radicals, which I've already sort of outlined. When you add or subtract, they have to have the same index, which means they're the same type of radical, and the same radicand, that is the guts. On the inside. So legally add, and ironically the only thing that you actually add or subtract is the outsides that are there already. Alright? So for example, if you had 5 square root of 3, then you were adding this to 4 square root of 3. Let's just check. Are they the same type? That is, they're the same index? Well, it's not written as a 2 here, but it is in fact a square root. and this is also the square root, so far so good. Do they have the same guts, same radicands? This is a 3 here and a 3 here, good, right? The only thing that you're really going to add once you have validated that is the coefficients, these two things. What's 4 plus 5? 9, square root of 3 is your answer. Okay, let's do one that involves subtraction. Maybe put it underneath this. All right, suppose you had this. 2 square root of 5 minus 6 square root of 5. And then you're adding the square root of 5. If, as is often the case in math, people being historically lazy, notoriously lazy, live on ones and decimal points and positive signs, and the indices of square root. If it helps, fill in the missing information. Like, for example, what number would you assume is really sitting in front of this if it's not written? I would assume it is a 1. Because if you put a 0 there, it's going to cancel out of existence. You want to fill in the missing information if you need it, if it's a convenience for you. All right. Anyhow, let's check. To add or subtract these legally, they have to have the same type index. This is a square root, that's a square root, that's a square root. They would all be 2's tucked into the index. Are they the same guts? Well, it's a 5, a radicand, 5 radicand, 5 radicand, so it's all good, right? We can legally add and subtract. What we must do are these two first. How come? Order of operations, right? You work from left to right. Subtraction and addition are equally important. So if the subtraction shows up on the far left, we do that first. Anyhow, just go, all right, well, what's 2 minus 6? All right, this is a positive 2. One of each sign would dictate that I do subtract, and you get a negative 4 square root of 5, right? There's still this hanger on here, which is technically 1, right? Now combine that. Right? If you have a negative 4 and you add it to 1, one of each sign dictates that you subtract. In spite of this sign, one of each says you subtract. All right, you're going to get 3 for the digit. All right, and it's still square root of 5, but what's the sign? Matches the larger one, larger magnitude, so it's negative. 3 times the square root of 5. Okay. Then there's this situation, right, where you lucked out to this point. You got things that match. You didn't have to change them too much. But you could still manipulate. Let's see. So let me give you the problem. All right. Suppose you had 5 square root of 3 minus 12. And it's a subtraction problem, so we would ideally do that. But you check first, right? You go, are they the same index? That is, are they the same type? Yes, it's a square root. Yes, it's a square root. Are they the same radicands, the same guts? No. And at that point, you might be tempted to go, frick this, I'm done, I'm out of here. But don't do that, all right? What you can do is you could attempt to factor this according to the product rule. All right. Again, ideally, you want to factor this into a highest perfect square, and then hopefully a number that matches, right? Here and here. So it would be 4 times 3, right? This much of it at least will escape the radical. What's the square root of 4? Well, it's 2, right? And then the leftover is square root of 3, which is great because it just so happens that we have the rest of this problem written as such. You have now the ideal situation. Identical type, index is 2, they're both square roots, and the radicands on L3. Anyhow, you have a 5, and you're going to combine it with the coefficient of 2. So it's really 5 minus 2, and your answer answer is negative, pardon me, it's positive because of this. So you would just say 3 square root of 3 is your answer. Okay. Multiplying radicals is easy, right? Because it's less strict criteria. You just have to make sure that they're the same index to start with. In upper level math, there's a way around that problem, but you're not responsible for that. Let's do multiplying radicals. Okay, so you have square root of 3 times the square root of 27. Okay, this is again involving the product rule, but the product rule is essentially in reverse. The product rule is about factoring, whereas what we're going to do instead is the opposite of that, which is actually multiply. Bring these things back together. Right? The criteria is forever, it will always be this case. They have to be the same index. They have to be the same type of radical, type of root. This is a square root, this is a square root. So what can you do with them? You can actually multiply them like such. And now you'll simplify it, arguably, because you're taking something that was expanded and making it more concise. All right. What's 3 times 27? 21, carry the 2, 81, which is great. Because what's the square root of 81? It is, thankfully, this number is a perfect square. So the answer is 9, actually. Okay, let's do another. Let's say that you had this. Square root of 3 times the square root of 13. You might hit a roadblock in the middle of the problem, but be determined, right? That's really the difference between anyone who fails and succeeds in math is just determination. Stick it out to the end. Try to manipulate what you have. If this, according to the product rule, more or less in reverse, is to actually combine these things by actually multiplying, right? Then you would end up with 39 here. 3 times 13 is 39. That is a crummy number, all right? But as an afterthought, you could maybe split it into different factors. In the case of 39, you would have to consider all the factors of 39, all right? And see what you have. All right, it would be 1 and 39. It's not going to be 2 and anything because it's not even. 3 and 13 is what it came from, so splitting that is not helping you. All right, 4 doesn't work. 4 times 10 would overshoot it. 5 doesn't work. It doesn't end at 5. 6 doesn't work because 2 doesn't work also. 7 times 5 is 35 is too short. 7 times 6 is 42. That's too much. 8 and 6 is 48. 8 and 7 is 56. That's too much. I'm sorry, I'm going the wrong way. 8 times 4 is 32. 8 times 5 is 40. That's too much. 9. All right. 9 and 4 is 36. Too short. All right. And 3 and 10. Well, that's pretty much it. That would be 30. Too much. All right. These are your limited choices that you have to work with. So using 1, even in spite of the fact that it's a perfect square, isn't going anywhere. You're stuck with this. Okay, that's the answer. Okay. Here's another one. Okay. The square root of 6 times 10. This will be a little bit more fruitful. We're going to combine these back together, and you're going to get 60. All right. Now, again, let's consider the factors of 60, and there'll be quite a few, right? There's 1 and 60, of course. It's an even, so it's definitely 2 and something. 2 and 3 makes 6. Add a 0 is 30. The sum of the digits would divide nicely with 3, so it's definitely 3, right? 3 times 2 is 6, with a 0 is 60, all right? 4 would work, all right? It's 4 and 15. 5 would work because it ends in a 5. It's 5 times 12. 6 would work because 2 and 3 work, so it's 6 times 10. 8 times 7 is 56, too short. 7 times 9 is 63, that's too much. All right. 8. 8 times 8 is 64, and 7 again is 56, doesn't work. 9, let's see. 9 times, 7 is 63, that's too much. And it's 10 and 6 again. These are your limited choices, right? And again, when you're trying to decide what would be a better choice of factoring here, we want the ideal situation being the highest perfect square possible. Again, virtually everything has the number 1 in it, but if you put 1 in 60, you're not making any progress. So you're never going to choose 1, all right? Another perfect square, if you analyze this list, is 4, all right? And that would end up being your best choice, all right? 4 and 15. How come? This is the highest perfect square possible. And it escapes. You know, some portion of it escapes. So it is 2 square root of 15. Okay. Now let's do division. And we're almost finished. Really got to clean this board. Okay. Let's see. The board is moving a bit. Okay. Here's dividing. Dividing radicals. Funny looking at this. Okay. Let's start with an example. This is basically, for right now, the initial problems. Using the quotient rule in reverse. Sort of like before when we're multiplying, we're using the product rule in reverse. It's not factoring so much. If you had this to start with, the square root of 75 sitting on top of the square root of 3. According to the quotient rule, this would have originated from something that looked like a fraction on the inside of just one big radical. All right. The advantage to going this way, sort of reverse, rather than, I would argue that this is forward, is that you could maybe simplify these numbers once they're together. Right? In this case, you do have the same criteria as multiplying. In order to do this legally, I'm going to use green, right? They have to be the same index. That is the same type. Anyhow, once inside, what's this divide? Think of money. What's 75 cents divided in 3? A quarter, right? So this reduces to really the square root of 25, which is just by itself a perfect square. It's 5. In an example of one of those less practical, more complicated problems, you still do the same thing. I'll put it here. If you had the square root of 60 sitting on top of the square root of 5, again, we'll apply the quotient rule in reverse. We'll combine these into one big radical, 60 over 5, because maybe I could shrink it down to something that will escape right away. In the last problem, at least, that's what happened. All right. What is just the, what does 60 divided by 5? It would reduce to this, 12, right? Now 12 is irrational. It isn't a perfect square, but maybe I could factor it. I can, perhaps ironically, now apply the product rule. So If again, I consider all the factors of 12, 1 and 12, 2 and 6, and 3 and 4, this is, you see, the reason why it's good to memorize information and do it faster. All right, I can very strategically choose 4 and 3. All right, again, this is the highest perfect square possible out of these choices, and this is just a leftover then. All right. This is going to be 2 square root of 3 is my answer, because the square root of 4 is 2. Okay. Now here's the more interesting thing, rationalizing. Let's see, I wish I had a different color. Rationalizing a denominator. I don't know how best to refer to this technique other than to simply say this is an example of good etiquette. Right? In math. That sounds silly, right? Because math is supposed to be very neutral, completely apolitical, completely asexual, right? But believe it or not, it has its own kind of etiquette, and this is an example of that. We, for all intents and purposes, do not like radicals in a denominator. Oh, I hate you, Green. You're making me hate you, Green. If we had our preference, we would not want to have a radical, regardless of what is on the inside, as part of a denominator that is down here, as opposed to whatever's sitting up here. All right. Sometimes the algebra and the arithmetic of calculation works out that way, and it isn't that the answer is wrong, but probably for the reason that we haven't always had calculators, and having an irrational number as part of a denominator kind of complicates further use of that. The trick was to rationalize the denominator, which is basically this. Create an equivalent expression. Right? Basically, one in which the radical is not, all right, a denominator. Okay. It will be equal to whatever the value overall is, right? If you typed in whatever the value is above the line and whatever the value is below the line, before and after, all right, it will produce the same decimal number, all right, but it will look different. It's totally superficial. It's etiquette, right? Because remember, etiquette is not based upon any sort of logic, you know, really. It's based upon aesthetics, right? How things look. It kind of looks nice when a person stands up straight. That's good etiquette. It looks nice when you don't put your elbows on the table. It looks nice if you speak very precisely, as I'm guilty of not doing. Anyhow, here's the strategy for right now. All right? You're going to basically, in a nutshell, multiply by a convenient ratio of 1. That is really essentially all that will be going on. Convenient for you. You decide that this makes things easier, all right? And it has to be equivalent to the value of 1 overall. It will be a ratio, which means it's going to look like a fraction. All right. Now, what that ratio actually is, all right, it's usually going to be this. It's basically the denominator, whatever it is, sitting on top of the denominator. In more complicated problems, there would be more to it, but the kind of problems that you're inclined to see at this level would be no harder than that. you're likely to see. Here, here's an example. If you had this as a problem to simplify, you would identify it right off the bat as, oh, it's a division problem, right? But how is it different from the type that you had done just a few moments ago? A few moments ago, there was a radical on the top. In this case, there is only a radical on the bottom. You can't combine these as they are, right? And we're already violating our own sort of rule here, which is, oh my God, there's a square root in the bottom, right, the denominator. So what do? Right? You multiply this times a convenient, I never know how to spell, a convenient ratio of 1. Meaning something that looks like a fraction. That's what a ratio is, a glorified fraction, really, right? But it's going to be convenient. It's going to make your life easier. You decide, right? And the overall value of it is going to be equal to 1. So what does that amount to really? Taking whatever denominator that you see and writing it on top of itself, right? So if the denominator here happens to be the square root of 2, then what you're going to write here is exactly that. The square root of 2 sitting on top of the square root of 2. Right. To make it a little bit easier to see, let me erase this and duplicate it underneath it. And I'll explain the intricacies of it. What I've done is this. I've taken the original problem that was written like this, and I've decided to multiply it by this convenient ratio of 1. I cannot stress that enough, right? The value of this junk that I have just thrown in here is ugly, right? It's the square root of 2 sitting on top of the square root of 2. But remember, it's something divided by itself. So what does it equal overall? This is really the value of 1 that I'm multiplying by. It's just disguised, right? Anyhow, that's what makes this legal. It may seem like you're pulling things out of midair, but it's okay, all right? As long as you're consistent, as I am fond of saying, all right? As often as the case in math, all right? You can get away with murder, all right, as long as you're consistent. If you start mangling the bottom of this somehow, manipulating it, all right, then fine. Just make sure that you do the exact same thing to the top, and everything is shipshape, all right? Everything is legal. If there was the square root of 3 here, then it would be the square root of 3 over the square root of 3. If it was the square root of 7, then I would make the ratio the square root of 7 over the square root of 7. How come? Because even though it's an irrational number, whatever the square root of 2 is, 1.41, something into infinity, it's something divided by itself. It's 1. It's taken advantage in a constructive fashion. Anyhow, normally when you multiply, it's the top times the top, and the bottom times the bottom. And I'm going to write the results here. 5 times the square root of 2 is simply 5 parked in front of the radical, like so. The bottom, there's a couple of ways you can muddle through. You could say, well, it is the two things combined. They're the same radical, index type, and the product rule would say put them back together, in which case it would look like this. Or as a side note, you could say, well, it's that thing squared, because it's something times itself. These mean the same thing, it's just two different perspectives. Anyhow, they will produce the same result. What is the square root of 4? Just 2 on the outside, which means that this is really 5 times the square root of 2 sitting on top of 2. If you looked at it from this perspective, there's 2 iterations of square root of 2, hence the exponent here. Well, those are opposite operations. What happens to opposite operations? They cancel, right? this cancels this, would leave you with the same exposed radicand. Now, here's another one. If you had 5 sitting on top of the square root of 12, we are still going to do this. We're going to multiply by a convenient ratio of 1. All right? As long as you're multiplying by 1, it's not changing the value of this. I just need to do it in a sneaky sort of way, in the style of a convenient ratio. Now, you could just use 12, all right? There's no sin in that, and then factor your answers as an afterthought. But you could be a little bit more strategic. I'll do this one 2 different ways. Let's say that you just went with what is tried and true and what definitely works, which is to go, well, whatever is here, the square root of 12, I'll make that my convenient ratio of 1, all right? In which case, you would have 5 square root of 12 sitting on top of the square root of 144. And to take it as far as I can, at least initially, the square root of 144 is just 12. I could have written it this way, right? I could have went, well, what's the square root of 12 squared? Right, and that cancels. That gives me the same answer. But look what happens at the top. This is applying the good etiquette. It's rationalizing the denominator. There's no radical here anymore. But it isn't completely simplified, though, if you analyze what the leftovers are. You could factor this, and unless you have the experience, you may not realize that. Anyhow, what can you factor 12 into? The square root of 4 times the square root of 3 again, which means that this much of it is just going to be 2 on the outside. Square root of 4 is 2. But you have to combine it with the leftover that is there. This 2 that is in front and this 5 that was in front multiplied together would be what? 5 times 2, the square root of 3, sitting on top of 12. All right. That, if you can combine those things, would make this 10 the square root of 3, sitting on top of 12. And even that could be simplified further. Right? If you just treated this as if it was an ordinary fraction, they're both even. All right? So you could definitely simplify by 2, each of these things, divide each by 2. Ideally, you want to go for the GCF. Coincidentally, it is 2. What's 10 divided by 2? 5. What's 6 divided by 2? Pardon me, what's 12 divided by 2? 6. The end result would be this. 6. Going through this thought process is totally cool, all right? Especially if you're just getting to learn this. You could be a little bit more strategic up in the front, all right? That is, when you're choosing the convenient ratio of what's going to be sitting here, 1, you might elect a number that you know is going to be a perfect square right off the bat, you know? That may also help you simplify. Here's what I mean. We know what the answer is, but let's see the option that we could explore here. Suppose that the convenient ratio of 1, to be a little bit more strategic, was not just duplicating what is here, all right? But something that would work rather nicely. Let's see. Suppose I went for this, the square root of 3 over the square root of 3. That is a ratio of 1, right? It's just not merely duplicating what is here. That will work. You've already seen it work, all right? What will happen if you combine this stuff now? Well, top times top, numerator times numerator is still 5 square root of 3. So far, so good, right? When you combine these strategically produce 36. All right, 12 times 3 is 36. What's the square root of 36 though? Goes right to the answer. It's a little less involved, a process, right? And how do you know to do that? With a lot of experience. You do a lot of these types of problems and you memorize a lot of stuff, which you should never be ashamed of doing, all right? Memorizing anything, all right? It helps you make predictions, right? It makes you more strategic. Okay. All right, let me leave it at that. As I said, I'm going to have the handouts posted so you can print them. All right. What I encourage you to do is simply this for homework. This was section 5.4. All right. Try to do section 5.4 in my lab. All right. This is through Canvas. Please don't do it through anything else. There have been at least 2 or 3 instances where I had a person, and innocently so I know, that they made an account not through Canvas, they made it through Pearson, who was the software publisher. I didn't think there'd be an issue, right? You shouldn't. I admit, you really shouldn't. But please do your work through Canvas, because unless you do, I won't see what the result is, okay? If for whatever reason, in 1 or 2 cases, I have a person not showing up in my roster, all right, please do continue to try to bother them. All right, they shouldn't be, don't be apologetic about it either. You paid for it. All right, just call them up and ask them, please, can you merge the 2 accounts? It's not rocket science. These people wrote the software, ideally. All right, anyhow, just try to do section 5.4 because that's what this pertains to. All right, I hope to see you at some point in the future. All right, take care, folks. I'll see you next week, at least this way.